All right, so who can tell me, like, real quick, where does this test start? What's the first thing this test is going to cover?
Probability.
So you know that chapter 3 is not going to be on this test, right? That's why I gave it its own little double quiz thing. It's going to be on the final, but not on this test. This test starts with the XP of X stuff and the binomial. I love that reaction. All right. You don't have to love it. You just don't have to know how to use it. Well, I wish you would love it, but you can only do so much. So the first formulas we can do. Now, of course, you can use your old formula sheet or maybe rewrite it if you lost some points on that last one. But you can just keep adding stuff. Right? You can just bring in every formula sheet with you. At the final, you can bring in all your formula sheets. I don't care. Yeah. So the whole idea, I love the teachers that make you do it on this little note card or something. And I'm like, when they get older, then they make people do it on grains of rice. So you have to learn how to, and then you have to. And they're just sitting there laughing at you. I don't know. Just bring in free. As long as you can put it on huge things, as long as you don't bother anybody, I don't care. All right? People around you probably be happy. Because I can see it. Oh, yeah. So the very first little dude, what's the mean for the XP of X stuff? Yeah, the sum of X times P of X. That's why the heaviest weighted thing is what affects the mean the most. If 70% of my data is 0, the mean is going to probably be close to 0 because that's going to pull it towards 0. So that's why the weight times the value, you add those up, you get the overall mean. We talked about where this formula came from. I always do that, just to show you where something comes from. Who remembers what the variance is for this situation? Yeah, that square is the most forgotten little square or little mean. I like it. And if you want to, I mean, if you want to just be doubly careful, you could put the standard deviation as the square root of all that, and, whatever you want to do. Right, this is the variance. You got to square root it to get the standard deviation. Want to be nice to yourself. And again, just to remind you guys, I would highly recommend you go double check these formulas for something written by a computer or something. You might read my handwriting incorrectly. Right? Use the wrong formula, it sucks. So that's one little section. Then the next thing was the binomial. This is when we're talking about discrete probability. So this was 0, 1, 2, that's in your face discrete. Binomial is number of people or number of cars. That's discrete also. You can't have 3.5 people had a flu. You can't. You can have an average of 3.5, of course. So the binomial, what's its mean? It's awesome. NP is no freaking, and times P. There's no freaking tables to make. There's none of that shit. It's awesome. Standard deviation, equally beautiful. Yeah, it's root of NPQ. NPQ. It's not in the modding device, really. And then you've got the probability formula. So remember, this probability formula is worse than it is, it's worse written out in general than it is specifically. I got a total of n things, and I want to choose x of them to be successes. So, of course, that means I have x successes, and the rest, that's the part that especially looks worse than it really is. Yeah, whatever the total is, I got to subtract the successes to see what's left over for the failures. In practice, that's actually pretty easy. If you have 28 people and you want 12 successes, then of course you want 16 failures. I mean, that's 28 minus 12 is 16. The formulas have to be more general. They're always going to look a little worse than they have to be in every single situation. All right, so that's another little section. So we do this is chapter 4. Yes, sir? You're okay, okay. Now I know in the homework, and I know even on the practice test, I have a question about the uniform probability. mean and standard deviation. I'm not going to write that on here because I'm not going to ask you a question about it. The reason I put it down, for example, I made you do it in the homework, and the reason that I put it down in the practice test is because when we do that sample size greater than 30 thing, it does not matter what it looked like originally. The standard deviation becomes the old one divided by the square root of n and blah, blah, blah. So if I have a uniform distribution, I got to use that weird-ass d minus a squared over 12 square root thing to find the standard deviation. And then I say, what about if I take a group of 43? Well, I take whatever I just got and divide it by the square root of 43. And then I can answer questions about the means of that. It's the same idea, Okay. So don't worry about putting the e plus a over 2 crap or whatever. Where am I at now? So that's chapter 5, basic was uniform probability. I don't think there's anything else in there really. Chapter 6 is where we start getting bread and butter. Normal distribution. That's where we bring back this dude here. You can also write it like that. It leads to this formula. For some of you guys, I think the people that can read that as a sentence are the people that don't really need to. They probably already know the definition of z-score. Because you know I'm going to ask you, I will ask you, on this next test, I'm going to ask you this question, what does a z-score tell you? Or I might ask you, what would a z-score of 2.7 mean? They're both the same question. One of them is a little more specific. Well, what does z-score of 2.7 mean for a data point?
2.7 standard deviation.
Yeah. So don't just say the amount, say more specifically, say that data point is 2.7 standard deviations away from the mean, or even a little bit better, above the mean because it's positive. I love it. Bless you. Don't give me an area, because even if I told you it was normal, does the z-score tell you an area? No. Chart does. Yeah. Right? A z-score by itself, I don't care what the distribution looks like, a z-score by itself tells you how far away from the mean to the data point in standard deviations. Right? All right, and then we've got, so I make that a little section. That's the classic z-score stuff. So that's chapter 6. And then chapter 7 adds in that guy. And if you want to, you can even write down I would suggest not, but you can if you want to. Our data minus the mean of those data points divided by the spread of those data points, it's the same stupid form. Right, if I take a sample and I ask you about the mean, what do you do before you calculate a z-score? You get the new standard deviation and put that down here. That's what the formula is saying. I like it. Aw, sharing music, that's awesome. You can do it. I just wanted to point it out. It was fun. All right. It's kind of cute. Anything else? Any other formulas you think we should put down? We should be able to put down on this formula sheet? Anything I left out? All right. This is it then. Okay. So no notes, no ripped bottom half of the page. No crossing stuff out with marker, right? It's got to be a nice full sheet. Nothing else except formulas. No notes, no weird little characters and go, that was just scribble. That's some kind of language you made up for yourself. That's happened before. I love it. Yes. Sort of. I'm like, well, that's awesome if you would have just done that somewhere else besides sheet and shit. Use that creativity towards learning shit. It's amazing. Shit. All right. So, the rest of the day is wide open. Anybody need a practice test? Good night. So So now it really is wide open to whatever you guys want to focus on. Oh yeah. You do one. You need one? Or you got a question? Okay.
On the practice test number 3, because I just want to make sure.
Oh yeah. Yeah, because number 3's got 2 parts to it. So be careful. So on the test, if I did that same kind of question, I'll put A, B, just make sure. So everybody got what they need from here? Hopefully nobody's screwed. So I think I didn't write anything. All right. So number 3 says find the z-score that has area of 91% below it. So of course, where would that z-score be relative to the middle?
The right side.
It's got to be up here if it's supposed to have 91% below it. The mean has what percent below it? 50, because the mean cuts the picture in for normal distribution, which is what we're dealing with, right? I like it. So it's got to be up here. I'm trying to find that z-score. What's this here? 0.91. What's another way I could have asked that same question? I don't mean like a different accent. Yeah, I could have said find P91. All right, this is P91. That's that kind of question. We've seen that before. That's the z-score that has 91% below. That's a quicker way for me to ask the same question. I like it. So what's really nice about this problem? The chart understands areas that are where? Below the z-score that I look up or that I want. And beautiful, that's the area below that z-score. I got to look it up. What's the closest I can get to 0.91? Did I bring a z-score chart for myself? You're so mean to yourself, Jeff. I'm going to have to... Hey! Yeah, the closest you can get... 0.9099. You can't get much closer to 0.9099. And that, what's z-score is at? 1.34. I like it. Take a minute right now. Make sure that you understand where that number came from. It's really easy to make more of something in this class than what it really is. It's just, if I can read this one way, I should be able to read it the other way. That's really all this question is showing. Okay, and the second part, some students make the mistake of giving me the same number again, but it's a different chunk. What's the second part of this say? Bounding the middle 91%, right? Chunk. So now if I look up 0.91, I'm not going to get anything related to this question. Because that is not an area below a z-score that I want at all. So then I say, okay, how do I use the area that this problem gave me to figure out the area below one of the z-scores I want? So what area is down here? Well, that's 91%. What area is outside? 9. So what area is down there? 4.5%. Do you guys see that? Why was that so easy? Because that's the middle 91%, and this picture is symmetric. Boogie, woogie, woogie. So if there's 91% inside, there's 9% outside, there's 4.5% on either side. So this is 0.045. That's another problem is people forget how percentages and decimals relate. So don't do that. Should know that by now. And then I do the same thing I just did. But the thing is, what's beautiful about this problem is if this, whatever this z-score is, this is going to be the same thing, just positive. Because it's symmetric. So when you look up 0.045, what's the closest you can get to that?
446.
Yeah, I like it. There's an option of 0.0455. That's 5 away. But 0.0446 is 4. Ooh, it's a winner. So, negative 1.70. I would actually also accept negative 1.695 if you split the difference. Okay. I like some of you guys like, I ain't doing that shit. All right, don't do that shit. I'll take this one too. So what's this one?
Positive.
Positive 1.7. If you don't believe me, what's the area below it? 0.955. You see that? If you get as close as you can to 0.955, it'll be positive 1.70. But why would you do that crap? It's metric, so you already got that answer. You guys with me? So this kind of problem is one we can do right now, but it actually is related to something we're going to be doing in Chapter 8. Creating what's called confidence intervals. So that's going to be in Chapter 8. We'll worry about it then. We could do homework problems too, quiz problems, whatever else. It's wide open. Whatever you want to focus on. Brandon's like, I'm just waiting to see what people ask. Don't worry about it. Yes?
1A.
Oh, yeah, okay. How many things do you have to show to prove a probability distribution is valid? 2 things. We should all know this so well after that quiz. Again, that's why quizzes exist. To make sure you're not going to make a mistake like that again when it counts for more.
Sum is 1.
Yeah. So you got to actually check that. So listen to me. You know this. Even before I say it, you somewhere in your brain, you know this. I'm going to give you a problem where it adds up to be 0.9999. Is that not valid? Of course it's freaking valid, right? Of course it is. It's just somewhere it was rounded. I just wanted to show you 4 decimal places and somewhere it had to be rounded. Do you understand? We've seen that before. This happened when we made histograms. Did we go, oh my God, I did everything wrong? No. We're just like, it's 99.5%. That's plenty good enough. Shit, I rounded. So don't just blindly say, now in this problem, the sum of the probabilities is 1. But on the test, it might not be. So don't just say that. I'll be like, you didn't even check. What the shit? Don't just know what to say. Know what to do, and then do it. All right? So you got to check to make sure the probabilities are 1 or close enough to 1. So if you add them up and you get 0.9, you're missing 10%. That's way too much, right? So I'm going to make it really clear if I did one way or the other way. One will be 0.9999, or it'll be off by like 12% or something crazy. Be really obvious, because some of you guys are like, well, where the hell's that line? I'm not going to go there. Don't worry. What's the second thing that's always going to happen?
Numbers must be between 0.
Yeah, the probabilities have to be between 0 and 1. Now, please, dear God, don't write this. This is so not true. Right? If I ask people how many TVs they own, you're not going to say, the number of TVs you own must be between 0 and 1. If you own more, throw some of that shit out. No. It's the probabilities that have to be between 0 and 1. The notation you use matters, right? Yes?
Doesn't the first one kind of imply the second one?
Not really, because you could have, the easiest way to do that is to say 1.5 and negative 0.5. 1. Right? It's like, holy cow, you get negative 50% chances. Yeah.
For the x p of x chart that we have, and then like the L3, like when you add up all those, it equals like the mean. When you add up all the L4s, what exactly is that?
That is a part of the standard deviation formula.
Is that like the variance?
So when you add up that last thing, you get this. And the variance formula is that minus the mean squared. So you add up that last column and you throw it into the formula, subtract the mean squared, you get the variance.
Oh.
Yeah, so it's just a step in the process of getting to. It's exactly like, and back in the day when we had this, I got a column of x minus mu's, right? I added them up, and what did I do? I threw it into the formula and finished the formula out. I get a column of these, I add them up, I throw it in the formula, finish the formula out. Standard deviation is always going to be a little more complicated because the idea of standard deviation is more complicated than the idea of the mean. So the formula kind of reflects that. You guys had me so excited. Several questions in a row. I was really excited. It's wide open. What do we guess? Which one? 1D? So once you get the mean and the standard deviations, let me just give you a problem like that, because I got the answer key for this anyway. Yeah. Let's do a problem real quick. A little tiny problem. I'll make them nice little numbers here. All right, it's valid. Those added to 1. They're all between 0 and 1. Beautiful. You guys with me? I'm just going to do a real quick little problem. I don't want to do that problem because I already did that problem. But the answer came good again. So 0 times that, 0, 1 times that, 0.3, 2 times that, 1.2. What is this? That's the mean. Because that is the sum of the xp of x's. The expected value, which is also known as the mean. So the mean is not 1. If you say the mean is 1, you're saying they're equally weighted. Are they equally weighted? No. And see how the mean was pulled towards the heaviest weighted thing. If they're equally weighted, it would be 1. That's heaviest weighted, it's 1.5. Got pulled up a little bit. Which is the same way, if you do really well on your test average, it's going to pull your overall average up. Because the test average is the heaviest weighted thing. And then this column is going to be who? X squared p of x. And I can do that by multiplying these together. Now what is that? What is this? It's part of the variance formula. It's specifically, it's the sum of the x squared p of x, right? It's the sum of that. That's what the column is. You can always take a second and identify what the hell you just did. So you do the right next thing with it, right? So then the formula says this thing minus the mean squared. So that thing is 2.7. The sum of these is 2.7. Minus the 1.5 squared. Who's going to help me? Okay. Point 0.45, yeah. Sigma squared is 0.45, so the square root by 0.673. What is it?
0.6703.
0.671? Sorry, I get excited when I know enough to get me close. And if I get lucky, I get really close. All right. So that is the standard deviation. Now, I finally can get to the question that somebody asked me earlier. I forgot who it was. You asked me about that last part. I couldn't really do the last part until I had some numbers to work with. So the last part says, what percentage, and we've seen this question before. We've seen this question before multiple times. What percentage is within one standard deviation of the mean? Well, what was the mean? 1.5. And it does say 1 standard deviation, right? Yes. So then if I add 1 standard deviation, where do I end up?
2.17.
Beautiful. And if I subtract 1, I'll end up at 0.829.
0.829.
All right. It's my one skill. I'm not. It's my one skill. So what did I just catch? I look at this. I don't like to fish. I don't eat fish because I hate the taste of fish. I do. So if you love fish, I'm not saying anything against you. Eat all the fish you want. You can have mine. But I always think about this like casting a net. So what did I catch? Did I catch 0? No. Did I catch 1? Yes, because 1 is right there. Did I catch 2? Yes, because 2 is right there. So I count all the 1s and all the 2s. I did not just catch 2 out of 3. I did not just catch 66.6 repeating. No, I caught all the 1s and all the 2s. So what percentage of the data did I just catch? 90%. All the ones is already 30%. All the twos add 60%. So I caught 90% of all the data. Fry it up and I give it to you. There you go. As I wear a gas mask. I don't have to spell it. Is that cool? So that's how you do it. You do the same old mean in the middle, go up and down a step in this case, because I just said one standard deviation. And then just see what you catch. The difference is you just look at the percentages. It's already done for you. You don't have to calculate it, you just add it. And you know, there always is a method to my madness. This is going to relate to something in chapter 8. An idea that we're going to talk about in chapter 8. But right now we can do this much. We know all the tools to do this. I like how some of you guys are watching me expectantly. I got nothing. Today is all up to you. If you don't need any help, then it's going to be quick. Yes?
On practice test 5B.
5B? B? Boy. So 5B, it actually sort of relates to 5A. So you got 24 adults that you've picked. So what are all the possible values for success? How many adults could be a success here? And this is, it doesn't really matter what this is, but it's an adult believing DNA tests for identifying an individual are very reliable. So how many people could think that out of 24? 24? 4? All right. So the quick way to write it, I love everybody writing every damn number out. You're hilarious, and you're like, well, you say, sure, you work 0 to 24. There, see? It's amazing. Don't forget 0. It's possible to have none of them think that way. It's not likely, but it's possible. Okay. Now, why do I do this? Because the question says probability X, what's it say, less than 22? Yeah. And how many calculations would that take for crazy-ass Jeff that will not let you do binomial CDF? Stop doing that. You'd have to calculate it for 0 up through 21, right? Because this does not include 22. Well, that's a lot of freaking calculations. And you can do that if you want to. And you can complain about the test being long, and I'll say you did that to yourself. Because what's the smart thing to do here? What's the opposite of less than 22 in this case? 22, 23, 24.
So then would 21 become our n instead of 24?
No, hell no.
No?
You can't escape 24 people in this problem. That's the setup. That's how many people I'm looking at.
But then 21 become the s?
No. What's the opposite of less than 22? Greater than or equal to 22. And what do I have to calculate for greater than or equal to 22? 22, which you already did in part A. 23, 24. So I just have 2 calculations versus 22 calculations, right? So I think I'd go that way. So remember, whenever the opposite probability involves less work, and very often a lot less work, hell yeah, I'm going to calculate that. That's not the answer. I got to do 1 minus to make it the actual question I'm asking. So I'm asking you to do 0 through 22 and add them up, and you say, no, I'm going to do, 21. And I'm going to do 22, 23, 24 instead, add them up, and then do 1 minus. Of course I'm going to get the probability of the rest. Of course I am, because altogether they add up to be 1. You got to be cool with that idea completely by now. So how do I calculate this? Well, I've already got probability x equal 22 from part A. Now I just got to do the formula for 23 and the formula for 24. Add those up and then take that away from 1. Yeah.
Already so good.
I I don't know. I think that's all right. Is that cool? So, I mean, what would the formula look like for 23? Choose 23. Yeah, what's the success probability? 88%. And I want 23 of those. So what's left over for the failure probability? 12%. And how many of those do I want? One. Right. Part A, you would have done the one with 22, 22, 2. You would have done that already. And then you also have to do 24, 24, 0. The probability of getting exactly 24. Add them up. That's the opposite question. So you do 1 minus to make it the actual question. Okay, cool. So where's the... You had a question on...
4D.
Yeah. Yes. Did you have something about this here, or?
No, I was just saying yes, because I was...
Oh, you have the same thing. Okay. All right. In case you're still copying something there. So for number 4, just starting off with number 4, it tells me that the mean is 281.2. Standard deviation of 34.48. Now it does tell me that they are normally distributed. Do I need to know that for Part D, actually? The only reason I just say that is because Part A, I'm only taking one student. So I have to know they start off normal, or else I can't do shit. I'm not going to do that to you. If you realize the answer is I can't do this, it's a little evil, because some of you guys might do all the work and waste time. So I'm not going to do that. Should do it. So Part D says if I select 33 students, find the probability that the mean of those 33 students is more than 315. So what are the two things that just happened that tell me what to do? Took a sample, and I'm asking about the mean of that. Oh shit, I better know how the means of samples of size 33, I've got to know how they're distributed. They're not distributed according to this, are they? No. Stupid things. They're distributed according to what? How do you get... It'll be the old one divided by square root of 33. This is how you create the spread, the standard deviation for groups of size 33. You take the one that works for individuals and you divide it by square root of 33. So if I wanted groups of size 78, I would divide it by square root of 78. And then I do all the same work, all the same z-score work, whatever. I just have to use that number because that's the one that works for groups. So how do I finish this out? The mean is 281.2. I want to know the probability more than 315. I, of course, do what? Yeah. Some of you guys like the whole, I got an X score, I got to make it a Z score, and then I can look up the area. Some of you guys forgot to look up the area. You just sort of circled your Z score. It's not good. So Z score would be, how do I set the formula up? Yeah, 315 minus 281.2 divided by whatever the hell that is. 6.002. I think it's 02. Past Jeff thought it was 02. That's what it says in my answer.
Sure.
Yeah, what do you get?
I got a 5.63.
5.63? Okay. And some of you guys might know what that means already. I mean, at this point, you need to understand what that number means. Is that an unusual thing?
Yeah.
Oh, hell yes. It is way outside of 2 steps, right? It's more than 5.5 steps above the mean. And every step is the average distance from the mean to the data points. So 5.5 of those suckers is way the hell out there. So you can go with what the chart says. It's stupid little about 0%, right? It'd be 0.999 and it'd be 0.0001. Or you can be smart and just say, that's freaking about 0. When I get way the hell out of 5.63, that's about 0% chance it's going to be above that. So if somebody was born and they became 9 foot tall, it's probably somebody's taller than that. It's basically 0 freaking percent. Holy shit, because we're still freaking about the 9 feet in the first place. All right, maybe. So you could either say about 0%. If anything's off the chart, you can say it's about 0%. Or you can do what the book does. It says 0.9999. You do 1 minus that, and you get 0.0001. Just really silly. Part of your brain should realize it can't be 0.0001 forever. It doesn't make any sense. It would add up to be more than 1 then. It's got to keep going down. Okay. So that is the 2 weirdness levels, right? You got to remember to change the standard deviation, and then you got to know what the hell it means when you get a z-score off the chart, and not freak when that happens. So if it would have been, what's probably x is less than 315, x bar less than 315, it would have been approximately 100%. I like it. Yeah.
How about 4C?
Okay. I thought people asked about 4B, but okay. 4C.
We can do that one after.
Oh, thank you.
Don't satisfy me.
4C. All right, so the top 5%. So 5% is a what? It's probability, I love it, which is also known as a what in this picture. It is in area. So that is this process in reverse. Right? Where would the top 5% be in this picture?
Oh, very right.
Freaking up there, right? So how do I find the z-score for that? Because now I got a percentage. I got to find the z-score because then I can use the backwards formula to get the x score. Yeah, good. The chart will only understands the areas below. And please, dear God, if you look at 0.05 and get a negative number, your brain should go, hey, whoa. No, it's up there. It should be positive, right? So you just take the negative off because of symmetry. But when you look at 0.95, that's when you should get the good old 1.645, right? And what formula do I use now to make it back into a test score? This is all about these test scores. I use the z-score formula, but you just use it solved for x, right? Because I know the mean, I know the standard deviation, and I just figured out how many steps I want to be away. If somebody scores this many steps above the mean, they will be in the top 5%. So I'm just figuring out what score that is. So, okay, that many steps above the mean. Okay, well, the mean was 281.2. Oh my God, Jeff. Plus 1.645 times 34.48. Gotta get that far above the mean to get into the top 5%. You could do the same thing for the top 5%. Heights, right? Whatever is normally distributed, you could do this kind of thing for. Is that cool, that one? If you're worried that I'm not finishing these problems, I'm going to give you the answer key in a minute. 4B relates to 4A. Do you guys see that? You can't do 4B if you haven't done the first part of 4A. So let me ask you this. If the probability that somebody still plays Pokemon Go is let's say 6%. right? So he's out there still trying to find a whatever, I don't know, char something. And I want to, and I say there's 300 people that were selected randomly. How many of them still play Pokemon Go on average? How many would you expect? What would you do? 6% of everybody plays Pokemon Go, and you have 300 randomly selected people. How would you figure out how many of them do that thing? You would take 6% of 300, right? Okay, now, you're all like, this problem says nothing about Pokemon Go. All right, but you see how 4A, you figure out the probability that a student scores more than 315. 4A1, the first piece of 4A. And then 4B asks you, well, if there's 2,000 students, how many of them would you expect to score? Okay, you got to know the probability first, and then you can multiply by 2,000 and figure out how many of them you would expect. So here, where that probability came from? Came from Jeff's imagination. Right? Here, to answer this question, where does the probability come from? From your work in the first part of number 4. So let me do this. Let me go ahead and give you guys the answer key. So if there's anything wonky on this, you can ask me about it. So. Can't be still going, can it? Yeah, really? Wow. It's probably about to stop.